Today, I'm going to present Scikit-learn on GPUs with our Array API. This has been in the works for around a year and a half, and there are many stages of this, and we're going to talk about them. So this is catered for people that use Scikit-learn and people that are interested on doing the same thing with their libraries and their code. All the material for this talk is available on my GitHub account, and the link on the bottom right here. So let's get started. So Scikit-learn and GPUs. I've been asked this question for the last 5 years, every year, for a long time, and the answer has always been no. We can't do this because of the complexity. So one of Scikit-learn's core principles is that we want the code to be easily readable for most people and easy to hack on. You could fork it, you could do whatever you want with it. And adding CUDA kernels is the opposite of that. So for a long time, we have not done this because of this complexity. Even our, we have FAQ, we get asked this so much that we have an FAQ entry just for this. Will you add GPU support? And then I'll read it. No, or at least not in the near future. The main reason is that GPU support will introduce many software dependencies and introduce platform-specific issues. So that's a historical stance, and we should update this because it's now time to change. But that's the reasoning. And the answer I usually give when people ask about Scikit-learn and GPUs is there's another library that I also maintain with another group of people, and it's called Scorch, where if you had a PyTorch module and you really want to use Scikit-learn's API, you could use Scorch, which wraps a PyTorch module, and then it has the interface of Scikit-learn, so you can mix and match it with any of the tooling around Scikit-learn model, because it's the API I use. Before I continue, how many people use Scikit-learn here? Okay, cool. All right, you're in the right place. Okay, so things have changed in 2022, so last year, in version 1.2. We added Array API support, and this added this for one estimator because this was experimental, and we want, this is new ground, and we want to explore the space. That means in 2022 we had support for NumPy and CuPy. So NumPy we always had support for, but CuPy is something new. That means we could, and CuPy only runs on CUDA on GPUs, so it runs on GPUs. But the API was not great, and I'll talk about that later in this talk about what the situation was in 2022. But things got better this year in 2023, where we enhanced our support for API such that the API for using enabling this in Scikit-learn is better. We also added PyTorch support. So now for the functionality that supports Array API, it's better now because, and we'll talk about the API today. So, at a high-level overview of today's talk, in the first part, I'll look at the user-facing API. If you're a user of Scikit-learn, how do you enable this, and what do you have to do to get this going on your machine? Next, so if you're a user, this is for you. Next, I want to talk about what Scikit-learn have to do to make this work. Because Scikit-learn traditionally only works on NumPy, and that means we had to transition from NumPy code to this new Array API thing. So there are certain challenges there, and to understand those challenges, I'm going to talk about the Array API standard itself, what it is, what the vision is, and to get the context of what Array API, and then I'll talk about the challenges right afterwards, all the things you have to think about if you want to do this transition. So, Scikit-learn API. Okay, so This is for users. So this is the example. This is a standard Scikit-learn code where you have a linear discriminant analysis. You could fit it on an ND array, and if you call predict on it, you get an ND array for NumPy. Very standard. Now the question is, where does the array API come into the mix? Well, there's two ways to enable it. There's a global configuration. So Scikit-learn has a global configuration object, and you could configure it by calling setconfig. Array API dispatch equal true, and you can see here that I'm creating PyTorch arrays on CPU. And if I pass this to linear discriminant analysis, at the end, you get a PyTorch tensor. So it's using all the operations that PyTorch provides to do this computation. So that's one way. The second way is a context manager. So you could, there's also a context manager. You could set array API dispatch equal true. In this case, I place things on CUDA, and so now it's running on PyTorch but on CUDA. And everything's exactly the same. It's the same API after that. Everything that comes out of this estimator is now a CUDA tensor. It's PyTorch tensor backed by CUDA device. So that's it. That's all you have to do. It's just the context manager. And why did we go down this route? Well, this is a slide at the keynote. It's benchmarking the code we were looking at before. And the blue bar graph is NumPy. It takes that amount of time, and when running on even PyTorch on CPU, it's faster than NumPy because the operations in PyTorch are parallel by default. So even though you're running on even though you're running on CPU, you're gaining the benefits of how PyTorch implemented its operations, and they're faster because they're parallelized, and they have SymD support, and they have OpenMP, so they do a lot of operations on the CPU code. Also on GPU, you could the GPU code that we saw before, it's also faster on a GPU, like much faster. So that's why one of the reasons why we wanted to try this out, because there's people have hardware on their machines, and we want to take advantage of it. And this is one way to do it. I ran this on a 16-core machine and on RTX 3090, so it's for these benchmarks. So that is the API. That's all you have to do. Like as a user, this is all you have to think about. Either do a global configuration or context manager. So if you're a user, that's it. That's the API. Now, the support is very incremental because we want to make sure that this is what the direction we want to go to. So at one point, we only have one thing supporting this, but this has been gaining traction over the last 6 months. Where in the 90 build we have it's growing. The list is growing, and when we release Scikit-learn 1.4, there will be support for more things. So and it's slowly growing, and we have community members that enabled PyTorch support for MPS. Like if you have a Mac machine, now you have MPS devices, and it's all going. It's going there. It's getting there. So this is the API supports. You can look at the documentation here on the bottom, and so to list out all the things that support it. So that's the Scikit-learn API. Now. I want to talk now. I want to switch gears. Or like, who here writes array code? Like they use NumPy or PyTorch in the day-to-day, like somehow. Yeah. Okay. So this is relevant to you. Like you write array code, and there's something called the array.js standard, which I'm gonna get into. And the vision of array API was that there are many array libraries. There's a subset of them here, and they all have an API. It's not a standard. CuPy and NumPy match almost work. It's almost matching, but PyTorch and NumPy, the APIs are similar but not exactly the same. Because if you want to migrate code from PyTorch to NumPy, you have to, or NumPy to PyTorch, you have to know the intricacies of PyTorch and know those APIs. The vision of the array API standard, which was built by this consortium it's called the Consortium for Python Data API Standards, and it's contained maintainers from these projects that got together to create a standard amongst the array libraries in Python. So that was the goal. It's a very ambitious goal because all the array libraries have different functionality. And so after a year or so, they created the standard. This is what the standard incorporates. It's focused on numerical computation, so numbers. Things like adding arrays, doing like simple math computation, like means and medians, creating arrays, things you think about when you deal with arrays. Broadcasting too from NumPy. The things that are not in scope are things that are not numerical I/O, like it's on this part of the slide. Thing to keep track of is that the types of like date times and strings are not part of the spec. So if you use ND arrays with strings, which I don't think you should because they're objects, you can't use the array API standard. So there's and the link has the full spec. It's just a big giant spec sheet of all the things that are in the specification. Now, there's also extensions to array API. There's extensions to array API. There's linear algebra, and there's Fourier transforms. Almost everyone does linear algebra, and that is what is important for machine learning. We need linear algebra for Scikit-learn and machine learning. So this is the thing that's what we need. And like all PyTorch, NumPy, CuPy, they all have linear algebra, so it all works. Yeah, but these are optional extensions. So, but libraries already usually include them because if you have an array library, usually you have linear algebra. That's like a given. So here's what the vision is and what the code, when the thing was developed, this is what the vision is supposed to be. You have some NumPy code. You see that it's calling NumPy, like np dot something, and then it's doing some computation. And the vision is, well, if you want to write array API code, well, instead of just calling NumPy directly, we grab the namespace from the array object that the user passed in, grab the module, and then from the module, call the functionality. So for PyTorch case, XP is just torch, and then if for CuPy's case, it would be CuPy, and so forth and so on. This is like the vision. This is the vision. There's like a precursor to that, right, when I say this is the vision, but there is. So during the initial release of this in 2022, it supported NumPy and CuPy, but not the ND arrays that you know and love, like np.nd array or CuPy.nd array. NumPy and CuPy created their own namespace with a different array object to support the array API. That means if you want users to use this, they have to know about this other object. And I didn't like that. Why, like, there's so many objects, why have another one? And it's kind of clunky. And we see that, we look at that in code. But yeah, so it created a new namespace. There was a reason for that. The reason was that the ND array namespace doesn't conform to the spec. So creating a new one is easier, but it's also harder for users because there's another object you have to think about. So to bring this point home, this is what array API support looked like in Scikit-learn 1.2 in 2022. So it's still the same API. You have some way to enable it, like in this case, a global dispatch with a global configuration. And users usually have their CuPy arrays. Like this is a standard ND array for a CuPy array. But then they also had to do like a transformation of the object to the conformant array. So like you see that I imported XP from like the CuPy.array API namespace. I also had to, users will also have to do this conversion too, to use the spec, which is not the best user API, and that's why I didn't talk about this in 2022. It's like a secret feature because this is I thought this API was horrible. And I think it is. Like who? Anyways, yeah. So it was, yeah, 2022. This is what it looks like. But in a collaboration between Meta and QuantSight, QuantSight developed a new package that libraries can use to make this a little better. And the library is called Array API Compat. And what this does is extends the Array API standard to the main namespace. So you don't have to go through this transformation back and forth between this other namespace and to the ND array object. So that's what Array API Compat is. It supports NumPy, CuPy, and PyTorch. There's in PyTorch currently. So that means the way you use it is what the vision, like the vision, what the vision had. Like the code from before with the vision is exactly the way you use Array API Compat. So you import array namespace from this library, which is a pure Python library. There's no compiled functions. It's a .py. It's very easy to install, and it incorporates the vision, and it works with ND arrays. It works with CuPy ND arrays. It works with PyTorch sensors. It also works with these other things, the other namespace, but I don't think people should use them on over here. So main users would be already using these normal ND arrays, and then you pass it to your library that calls array namespace, and it will just work with some challenges, which we'll talk about in the next part. So stepping back, Array API supports. This is what it looks like. This is what this slide I showed you. You don't have to go through this exchange between two different objects. It just works with the original, in this case, tensor, the PyTorch tensor, and this just works. So that is Array API. So with that context, I hope you're all motivated to write your code using the Array API standard. Like how many of you have maintained NumPy code right now? Like you have NumPy code or PyTorch code, and you deal with it. Like, and you work with it on your day-to-day job. Well, and if you want to write it in Array API, this is the challenges you will face when migrating. A subset of them, not all of them, but some things I want to highlight. So overarching, the challenges are there's API differences between, if you use NumPy code, there's API differences between the NumPy code and Array API standard. There's semantic differences, which means things that work in NumPy, if you change nothing, it would not work in Array API, and we'll see what some of those things. And then compiled code, which is a very big item. How many people have compiled code in their library or in their packages? Compiled code? Okay, so we're gonna have a fun time in that section for you, just for you. So API differences. Okay. API differences. So NumPy for the API, most methods are on the module or in the module. What that means is, let's say you have code where you call this y is a ND array and you call sum. This does what it does. It does what it says. If you want to migrate this to Array API, you have to there's not many methods on the object. You have to actually go to the namespace and grab the operation. It's not that bad. It's not that bad. This is fine. Everyone can do this. Where it gets a little annoying is when you chain them. Like if you're doing this is what it looks like. It looks kind of nice. You're just taking the mean, and then you're doing a Boolean operation, and then you're calling any. If you want to migrate this to your API, you have to kind of nest them. It's not too bad, but you can tell like, if you keep on expanding this, it kind of gets a little gnarly. Like, it doesn't look as nice, but it works in the API. This is what you have to do. Another thing is that matrix notation. If you use np.dot, that doesn't exist in array API because historically, np.dot does too much. np.dot does like, if you have 1D ND arrays and 2D ND arrays, it does something else, and you have two 1D arrays, it does too much. So in array API, there's no dots. There's just matrix notation. So this is also a simple one. So in this case, it restricts the dimension to be what you have to be to do matrix notation. It doesn't do all the complexity in dots. So these are the simple ones. These are not too bad. Unique is np.unique is very commonly used in Scikit-learn because when you pass for a classifier, when you pass classes into Scikit-learn, it needs to know what other classes are, so it calls np.unique. And for NumPy, this np.unique has it gives you the uniques, and it has many different of these return parameters, and which gives you different, depending on what you set, it gives you different return options. Array API doesn't have unique, it has a different word for them, like a different method name. And this is it's a common pattern. Like every API sometimes has different method names in NumPy, so you have to transition. It also doesn't have these return keywords because if I put on my software design hat, having a keyword argument that changes the number of arguments that your function returns is a bad pattern. So Array API doesn't have that either. So you need to call unique counts. So differences in API. We run into in Scikit-learn where there are some NumPy functions that are useful that are not in Array API, like NaN max. Like this doesn't seem too bad. It's the max, but ignoring the NaNs. This does not exist in Array API, and the way we worked around this in Scikit-learn is that we define our own on the Array API spec. So if it's a NumPy array, we just call NumPy. If it's a Array API standard array, we define our own based on the standard, and that's what we have to do. There is an issue open on Array API. They're very receptive of this, where you could, if there's something you need, open an issue, and they're considered put into the standard. This has happened before. We needed something, we open an issue, they put it in the standard, it's great. So they're very receptive to adding new things to the standard. This is one of them. So in this case, I'm doing integer indexing. I'm just indexing some rows, 0 and 1. Doesn't work in Array API. You need to use a method. Integer indexing with multiple indexes and with a list doesn't work. You have to call xp.take. This is very common in machine learning, where you're shuffling things or you're sampling things. So we needed this, and so they added the standard in 2022.12, not through indexing, but using a operation, which is okay. It's not too.
That's hard to detect because sometimes it's programmed, right? And you don't pass in literals, you may pass in a variable that computes that, so it's not that easy to detect.
Oh, that's true. So if you do this in your API, it will error. So you have to pass in array type compatible arrays and no error, and then you can detect it. But it's iffy.
Yeah.
But the thing is, xp.take, it also exists in NumPy, so np.take also it already exists in NumPy. So it would just be compatible with NumPy anyway, so it's fine. It's okay. The other part is that this part where you have to think. The API standard likes to work with arrays. So you can't use a Python list anymore. You have to use an array. Right? So okay, so they're getting more and more challenging as I go, So we're gonna keep going. Multiple dimension. So this is a 2D ND array. I just want the index 1 row. Right? So I just do this. This is fine, right? This looks fine. Doesn't work in array API, but it's not too bad. It'll give you an index error, and it'll give you and where you have to specify the other dimensions. So it doesn't assume that you want all of everything else. You have to put in this colon to say I want the rest of the columns. All right. There's a lot of little nits here.
Who came up with that? That is so assumed.
I'll answer the question afterwards. But who uses random number generation? Like that's the thing. Well, doesn't exist in array API. So this is NumPy random number generation. What Scikit-learn does, because a lot of machine learning, you instantiate a model of random numbers. It's a very standard thing to do. What we end up doing is we use NumPy as a random number generation, and then we converted it into the array API spec. It works. It works. Okay. This one is a little. Who cares? Who knows about order for ND array? Okay. This is for you. Order is a thing. C ordered means that when you this is a 2D array. C ordered means that if you traverse the array left to right in memory, the data is right next to each other. So yeah. And if you F ordered means that if you traverse the array up and down, the data is right next to each other. So that means that if you're writing NumPy code and you want to sometimes optimize more for it, let's say you're summing over going up and down and summing over the columns, going up and down, that means that an F order array is faster because the data is right next to each other, so the CPU doesn't have to jump. So this is a common thing to do. Like this, we do in Scikit-learn sometimes because we're a machine learning library, we want to be proficient. Order doesn't exist in array API standard, so there's no hack around this. You can't do this. So, there's no notion of order in array API. Okay, so I don't have a good workaround for this. Okay, I went through a few of the differences that I think are important. There's a lot. There's a great page about this on NumPy docs. If you want to look at the difference between the array API standard and NumPy, this is what you have to look into. It's a really long page. It's very well written. It gives you all the differences. Oh, okay. Next, semantic differences. Which is things that work in NumPy code that doesn't work in array API code if you change nothing. So in this case, I'm adding an ND array that's integers and ND array that is floats. Oh, this means so NumPy will upcast the integer to a float and add them up. Array API will error. It will not upcast for you. I think this is better. For this case, I think this is a better. In principle, I think this is better. Not upcasting. Upcasting leads to many performance things because you have to memory copy when you upcast. So I think this is a better default, but it's a little annoying. So the workaround is you have to do the casting. You have to explicitly cast up before you can add to NumPy. I think this is better default, but you still have to go through this hurdle. when you use NumPy arrays, it's very common to use it with Python scalars because you're in Python land. So this also applies to Python scalars. So this is a NumPy array that's integers. I added to a Python float. This is fine in NumPy. Type error in array type standard because no upcasting. So the same workaround. You have to type your ND array for it to work. One more thing is array creation. So when you work with array library, you very often create arrays. So in the top, I create a ND array with linspace. Linspace also exists in array API. This one's not too bad. Well, for the array API standard, you have to be careful about pasting things on the device that your user passed in. So if your user passed in a CUDA array, back to a CUDA device, you have to make sure all the new arrays you formed are also backed by CUDA because you want to operate between them. Like you need a CUDA array to work on a CUDA array. So you have to pay attention to when you create these create new arrays, make sure they have to create the right device. That's another thing. So this is standard. This makes sense. So that's for device. Okay. So compile code. This is a big one. This is compile code exists in many places. In Scikit-learn, they're in the tree algorithms, the efficient gradient boosting algorithm, the linear models. Linear models uses SciPy, which uses SciPy to optimize, which uses Fortran code, which is compiled. So, there's compile code everywhere. And array API standard is a Python specification. So it doesn't touch compiled code. So we've been thinking about workarounds for this. The solution that works now and that SciPy has implemented is that that only works on CPU arrays is to convert from NumPy and back. Convert to NumPy and then go back. So what this looks like is, let's say you do some array API code up above. Convert your array back to NumPy, and then have your compile code that works with NumPy work on that, and then afterwards convert back to the array API object. And it works. It only works with the with CPUs because the compile code only works on CPU. So that's that. So SciPy is currently doing this now. There's been attempts to do this better because we want to dispatch to compile code that is not just for CPU. We want to dispatch to GPU compile code too. Somehow, there's been attempts on this. SciPy has UArray, which has not panned out, simply put. Scikit-learn is experimenting with something called plugins, which is not in main yet, but it's we'll talk a little bit about it. So this is the thing in discussions with SciPy, they look like they're thinking about doing this one, which we'll talk about quickly in the next few minutes. So dispatching with, let's say, plugins, it's what it says. A third-party library, maybe developed by someone else, could create a plugin to write the CUDA kernel, and then we dispatch to it. That's what it does. Array API is still important in this use case because it's very frequently that you do compile code somewhere. You do normal Python operations before you compile code, and then you do some normal Python operations after. So you only dispatch for the compile code, and the API has a standard for doing things that are in Python land. Next, the array library specific code. The standard has a specific set of operations, but many of the array libraries implement more than the standard, and it's shared between them. So, for example, Earth is a It's an integral, and you can dispatch to NumPy, CuPy, PyTorch, and to Earth. So that's something that SciPy is thinking about doing. So it's a library-specific code. So those are the challenges. There's a lot of them. Why? I'm putting my sales hat on now. There's a smaller API because it is smaller. It's portable, and performance. Yeah. So these are the main reasons why API standard was adopted. It was for this graph to make this work. SciPy is also adopting this. They use environment flag. These are the things that supported in SciPy now. So SciPy and Scikit-learn is slowly adopting this now. You can read more. If you're a user, try out the feature in Scikit-learn. If you're a library author, you're welcome to try out the API standard. You can open an issue on their. If you have a function that you need, you can open an issue on their issue tracker. And everything here is available on my GitHub account. It's public. And thank you everyone for listening to the talk.